class, this is Mrs. Gallegos, and today's lecture will be on topic 4, section 4, intermolecular forces. What is an intermolecular force? Intermolecular forces are also known as van der Waals forces. Now remember, we know about the covalent bond, and it is a strong electrostatic attraction between the atoms of a whole molecule. Intermolecular forces, however, occur between molecules or in between covalent molecules only. And these are weak electrostatic attractions, and that's why they're represented with a dotted line instead of a solid line. And we are going to be making a lot of connections between intermolecular forces and bulk physical properties, those physical properties that we can observe where a large amount of particles are involved. And these examples of these bulk particles would be melting or boiling point, solubility, or volatility. So let's look at the volatility of water compared with isopropyl alcohol. Watch carefully, and hopefully by the end of this video you can explain your observation. On the left we have water, and on the right we have isopropyl alcohol. Now think about what's happening. This is a bulk property, volatility. What's happening between the particles to explain that? Why did the isopropyl alcohol evaporate before the water? Okay, let's dive into intermolecular forces. So what are the different intermolecular forces? We have London forces, dipole-dipole interactions, and the hydrogen bond, which is a misleading term. It's not a bond like those strong electrostatic attraction, the ionic bond or the covalent bond. It's still an intermolecular force, a very weak electrostatic attraction. All right, so let's start with London forces. What are the London forces? Well, the London forces are also called dispersion forces or instantaneous dipole, induced dipole. Now, what does that mean? The London forces, first of all, were described by London, who was, I believe, a German Jew who was forced out of Nazi Germany and ended up teaching at Duke University. And so London described this force of attraction. It's a temporary change in electron density that creates a temporary dipole. So if you look right here at letter B, we have a symmetrical density of electrons around the proton. Now, every once in a while, you'll have a disruption in symmetry, and one side of the atom or the molecule will have a greater electron density than the other, and then a temporary, so you'll have a non-symmetrical density of electrons. And so this creates a temporary dipole. And so the temporary dipole will then induce a dipole, and so it will induce a non-symmetrical density of electrons in an adjacent molecule or atom. And so as soon as I have a dipole in both, a temporary dipole, and then an induced dipole, and two molecules or two atoms, I can then have a weak attraction between these two temporary dipoles. Now remember, these are not permanent dipoles like we've seen in a polar molecule. So generally, you'll see these dispersion forces, and the reason why it's called dispersion forces is because the electrons temporarily disperse non-symmetrically, so that you'll end up with a negative temporary charge on one side and a positive temporary charge on the other end. And so that's why they're called dispersion forces, because it's the uneven or non-symmetrical dispersion or density of electrons. Now this is the primary force of attraction between nonpolar molecules, because nonpolar molecules are that. They don't have a permanent dipole but they can have a temporary or an induced dipole. So it's important to remember that dispersion forces exist in all atoms or molecules because they all have electrons that could have a temporary non-symmetrical density. So London forces are found in all between all molecules. However, they are the only force that exists between non-polar covalent molecules. So what affects the strength? So not all London forces have equal strength. So the first thing that affects strength is the number of electrons. So if we look at the family of the halogens, we have chlorine, bromine, and iodine. Chlorine has less electrons than iodine. And so we're going to call the electron cloud in iodine more polarizable. And the reason being is that the valence electrons are farther away from the nucleus, so there's less of an attraction, so I can more easily move those electrons to one side of the atom or the other. And then I simply have a greater number of electrons, so the magnitude of that temporary dipole will be greater. And so the intermolecular force between iodine molecules will be much stronger than this London force between chlorine atoms. And so I'll represent this with an arrow, and you'll see that iodine, because its electron cloud is more polarizable, meaning that the non-symmetry is easier to induce because of the less attraction for the nucleus, and the fact that there's more electrons means that the magnitude of that temporary dipole will be greater, so therefore the intermolecular force between iodine is much greater than chlorine. So we can see that at room temperature because chlorine is a gas, and so we know that in gases, the particles are very far away from each other, and that's because there's not that great of a force of attraction between chlorine molecules, where bromine is a liquid at room temperature, and iodine, or iodine, is a solid purple crystalline at room temperature, showing the greatest intermolecular force, or this great London's force. And notice we know that there's no permanent dipole here because these atoms' electronegativities, these molecules' electronegativities are zero, because iodine's electronegativity minus iodine's electronegativity, of course, will be zero. And so if we look at the melting points, we see that, or the boiling points, we see that the halogen, which I haven't shown you a picture of, has the lowest boiling point at negative 188, and then chlorine, which has a more polarizable electron cloud, so its IMF, its dispersion force will be much greater, so it has a boiling point higher at negative 35, and then bromine, again, has an even more polarizable electron cloud because there's more electrons, and those electrons are not held as tightly by the nucleus, and so bromine has the highest of boiling points, and you can't see it, but iodine has a boiling point of 184. So this bulk property is influenced by the strength of the dispersion force between chlorine, bromine, and iodine molecules. All right, so the second thing that affects the strength of the London force is the size of the molecule. And so if we look at a series of molecules where the number of carbons and hydrogens is increasing, we know that that molecule is getting larger, and that means there's more electrons. So the electron cloud is also larger, and so I have more polarizable electron cloud. And so if you look at the boiling point, again, this is the bulk property that I can link with the difference in the London force. And then notice once again we have carbon-hydrogen bonds, which are very weakly polar. And so even though there is a slight polar, could be a slight polar attraction, the London force is much stronger, as you see, because the boiling point of methane that has just one carbon is negative 161.6 degrees Celsius. But if I look at octane that has 8 carbons, a much larger molecule with a much larger polarizable electron cloud, has a boiling point of 125.52 degrees Celsius, which means that the London force is much greater with an increased number of carbons. And more electrons. So the last thing that affects the strength of the London force is the shape of the molecule. And so if I look at, these are called isomers, which means they have the same number of carbons and hydrogens, but they have different structures. So if you look at normal pentane, it has a linear structure. Isopentane has one of the carbons that's bonded off another carbon. And then tertiary pentane, or 2,2-dimethylbutane, has almost like a four-leaf clover shape. But they all have 5 carbons. And so we have different shapes here. And if you look at the boiling points, we can tell right away that pentane, since it has the highest boiling point, must have the strongest London forces. So we can then infer that if you have a larger contact area in between adjacent molecules, then that London's force is going to be greater. Whereas if you have these branched carbons, like isopentane, one of the carbons is branched off another, and in tertiary pentane they have 4 carbons branched off a central carbon, there's less contact area, and so the dispersion force will be weaker. And so if we look at this series of melting points, we can see it a little better. We have, in the first two, we have an example of a small volume and a large volume, and we see that the CH4s, because their electron cloud is less polarizable, they will have a weaker London force and boil at a much lower temperature than the pentane, where they have a larger polarizable electron cloud. Then if we compare the boiling point of the pentane, which is in the middle, to an isomer of pentane, notice that's the tetrapentane, where we have still 5 carbons with a different shape. We can see the boiling point of that is 9.5, meaning that the contact area, the shape of the molecule, pentane, allows for a greater contact area than the shape of the other pentane. So the 3 things that affect the strength of the London forces are the number of electrons, which means the polarizability of the electron cloud, the size of the molecule, which means larger electron clouds mean a greater force of attraction, and then the shape, so how much contact area do you have in between adjacent molecules. The next intermolecular force is the dipole-dipole attraction. This dipole-dipole attraction exists between all polar molecules that have a permanent dipole, and here on the right we have an example of HCl. We know that hydrogen will have a positive charge, and chlorine will have a negative charge, and the same with another hydrogen chloride. And when they are adjacent to each other, the chlorine will have a weak intermolecular attraction to the hydrogen. And since both of them have a dipole, we call this a dipole-dipole attraction. And again, it's represented by a dotted line. And we notice that the greater the difference is between the electronegativities of the positive and negative charges in the dipole, then the greater that intermolecular force is. So what is a hydrogen bond? A hydrogen bond is a special type of dipole attraction. It occurs only between only between the polar bonds hydrogen fluorine, hydrogen oxygen, and hydrogen nitrogen. So first we have the oxygen, hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen donates a hydrogen to the bond. And then we have another molecule that has either an oxygen, nitrogen, and fluorine on it that accepts the hydrogen bond. And then again we see that intermolecular force represented by a dotted line. Now the hydrogen bond is the strongest of the intermolecular forces, dispersion being the weakest. Again, over here we have an example. We have water and ammonia, where in this case the ammonia, the NH3 hydrogen, is the hydrogen donor to the hydrogen bond, and then we have the oxygen of water as the acceptor, and there's my hydrogen bond. Down below we have the very important molecule, DNA. Do you remember learning about DNA having hydrogen bonds down the middle of the double helix? And so here we have an example of the G and C guanine and cytosine pair. And we can see that we have the hydrogen donor on one side of the DNA, and then we have the hydrogen bond acceptor, and there's my hydrogen bond. And in this case, between guanine and cytosine, we're going to see that there are 3 hydrogen bonds. So hydrogen bonding is, of course, very important to living organisms. So going back to our original video, I want you to apply what you've learned about intermolecular forces, both the dispersion force, the dipole-dipole attraction, and the hydrogen bond, and see if you can come up with an explanation for why it is that isopropyl alcohol, which is the structure shown on the right, had a much higher volatility at room temperature, which means it evaporated first. It has a higher volatility than water. And we'll discuss it when we meet next.